All right, in this lesson we're going to look at two examples of circular motion. In the first example, we're going to look at the normal force actually acting as the radially inward force, giving us our circular motion. And in the second example, we're going to look at an interesting problem called the conical pendulum, but we'll get to that in a moment. The first example we're looking at here is that amusement park ride, sometimes called the Gravitron. How does the Gravitron work? Well, you step into the Gravitron and you are standing on the floor. So initially the floor is right here. You were standing on it. And it's not spinning yet, but now they spin it really fast and then they drop the floor. So the floor goes down to here and then it disappears from here and you are magically stuck to the wall by the radial forces that are acting on you, and this is what we want you to understand. Why is it you are stuck to the wall? Well, what you feel when you're inside the Gravitron, and if you're not really thinking about physics or what's actually going on, you think you are being pulled outward by this centrifugal force, which we never want to put into a problem or show the AP grader. So remember what is actually going on, right? What is actually going on is that there is a radially inward force only. It has to be an actual radial force. Tension, friction, gravity. We're going to see the force normal in this problem. But there has to be a radially inward force only, no outward force. And of course, the motion is tangential. So this outward pull that we think is there is actually not there. That doesn't happen. All right, well, what is going on? Well, gravity is certainly going on. So if we go back here for a second, we have gravity pulling you down, but your feet are above the floor. So what's going on? Well, you're moving in a circle, right? So you're moving in this circle, and it is the normal force. So that outward pull perception you have is actually coming from the wall pushing radially in on you because the center of the circle is here, and you spin around. And it's the force normal pushing radially in which gives you your necessary radially inward force allowing for circular motion. Well, the only thing then that is keeping you from going down with gravity is the friction between your back and the wall. And we know friction is mu times the force normal. So we now have a normal force because the wall is pushing radially in on you. So if we have a coefficient of friction, you will stick to the wall. So the most important thing in building this amusement park ride for the people that build it and run it is to make sure that you have a relatively rough surface on the wall so you have a high coefficient of friction to allow you to not get pulled down with the floor. We'll see it really has nothing to do with how big or small you are. Adults and children alike should be able to stick to the wall. So let's see what's going on in terms of numbers. So I put the equations down first in terms of the equations, the F equals ma equations, in the radial direction and in the y direction. Now in the y direction, we want friction and gravity to balance each other. So in the example I have here, numerically, I put in 40 kilograms, but we don't really need the number at the moment. We could go back and talk about it numerically if we want to. But we have friction upwards, so that's why it's positive, gravity down, mg equals 0. Radially inward is always our positive direction, and our only radial force is the force normal, so radially inward equals mv squared on r. So these are the two equations we will always use to solve this Gravitron problem. Well, if I'm designing the ride, what are my considerations? Well, mechanically, I probably can only spin it so fast, so that will correspond to the v. Remember, I'm going to spin it at a constant rate. So in this case, v will equal 2 pi r over the period of motion, or 2 pi rf, the frequency, depending on how my ride is specified. To get the speed, the radius of the ride is going to be fixed. Here I put a 5-meter radius in, but again, that doesn't really matter unless we're solving a specific problem and talking numerically. So once I know the speed that it operates at and the r, now I can begin to think about, well, how am I going to figure out what coefficient of friction I need? Well, I'm going to take this force normal and I'm going to plug it in over here. So that's where the m v squared on r came from in this red equation at the bottom. And notice the m's now cancel out. I can factor an m out of both of these terms, both this term and this term. So the m's come out, and 0 divided by m is 0. So this is why it doesn't matter whether it is an adult or a child. The mass of the adult will be much larger than the mass of the child, but that doesn't matter. I can solve this equation for the coefficient of friction. So the coefficient of friction will equal mg times r divided by v squared. And that would be my design equation where I would know this is the coefficient of friction I need for a radius and for the v that my ride is operating at. So, standard problem in introductory physics classes, this gravitron problem. So please make sure you understand all the considerations that we just discussed. All right, now our very interesting conical pendulum problem. Our conical pendulum problem is really tetherball. So I probably never thought of tetherball as a conical pendulum, but if you think about it, it's conical in shape in terms of the cone that it makes, so that we may have considered in the past. So we have that conical shape here. And when it's spinning around, right, so when it's spinning around this dashed circle, there really are only two forces ever acting on the mass. So the gravitational force is always straight down the whole time as it spins around. And the only other force in the problem is the tension in the string, which tensions pull, never push. So if we look at what is going on here, the angle theta up top here that it makes with the pole is the same as the angle theta here. So what we are going to get is a tension sine theta radially inward, and we need a radially inward force always for circular motion. And we also have a tension cosine theta up, balancing gravity going down, so that's why the tetherball will not move up or down. We then do as we always do. We're going to set sum of the forces equals mass times acceleration in the y direction and set it equal to 0 because the tetherball is not moving up or down. We have an upward force t cosine theta minus mg equals 0. In the radial direction, sum of the forces in the radial direction equals mv squared on r, always for circular motion, and we have to have a net radial force inward, so I'm making inward my positive direction. Here we only have one radially inward force, and that's t tension sine theta equals mv squared on r. So what we are going to do here to look at how we would analyze this system in terms of the parameters for designing a tetherball type of a system, we are going to take equation 1 up here, equation 1, solve it for tension, so we get mg divided by cosine theta, and substitute that in to equation 2, as I have shown here. So what we get then is mg on cosine theta in for f of t times sine of theta equals mv squared on r, and look at this. The m's cancel out. Sine on cosine, if you remember from trig, is tangent. So we get g tan theta equals v squared on r. Now, this is definitely not a formula you want to memorize, but you want to understand how the analysis and the force diagram and looking at the circular motion relative to the equations we have to use in Newton's second law allow you to very quickly, if you need to derive this equation. So you're going to have some homework problems looking at circular motion, and hopefully these examples have helped you out.